Next video on complex numbers for ASFurther maths. So this is our second video. So it's just talking about complex numbers as opposed to imaginary numbers, which we dealt with in the first section, and then a wee bit of manipulation of those as well. Then so it says you will notice from quadratic equations above the solutions are the form a plus or minus bi, where a and b are real numbers. Any number of the form a plus bi, where a and b are real numbers, is called a complex number. A is called the real part, that's this bit here, and b is called the imaginary part. You can write that the real part of a plus ib is a, and the imaginary part of a plus ib then is b. If b is 0, the number has no imaginary part. For example, 7 plus 0 is 7, so it is a real number. Real numbers are a subset of the complex numbers. Likewise, if a is 0, the number has no real part, and you get a pure imaginary number. So imaginary numbers are also a subset of the complex numbers. A set of complex numbers is denoted then by C. So adding and subtracting complex numbers, this is nice and straightforward actually. It's as simple as you would hope it would be. Sorry, I've gone up slightly too high. There we are. You can add and subtract complex numbers by adding the real parts and adding the imaginary parts. You can subtract one complex number from another by subtracting the real parts and then subtracting the imaginary parts. It really is nice and straightforward. Won't spend too long on this. Example 1. Then let's take a wee look. So the real part here is 2 and 7. So that gives us 9. 3i take away 6i is minus 3i. Taking these away, I guess you just need to be careful with your minuses. Other than that, again, very, very straightforward. 25 take away 13. That gives us 12. And then minus 7 minus minus 4. So that's minus 7 plus 4 effectively. So we have our minus 3i. Multiplying one complex number by another, again, it's not too bad. You just need to think about it a little bit. If you wish to multiply two complex numbers together, we use the rules of algebra. It's effectively FOIL we're doing here. Now we're multiplying this one by this one. So first gives us AC. Outer gives us IAD. I've brought the I then to the front. Inner IBC. And then last is I times I, which then gives us BD. So let's take a look at this. So that gives us then AC. Bringing together these two parts, you take the I out. So that's going to be our imaginary part. And then I squared, if you remember, I is the square root of minus 1. So if you square it, you just get minus 1. So that's a minus 1 there. That's why that then becomes a minus BD. And then that bit becomes real as well. So there's no I part attached to that. So we have AC minus BD equals I upon AD plus BC. So let's try the example on that and see how we get on. So this one says multiply 4 minus 3i by minus 7 plus 5i. So let's go for that. Just doing our FOIL here. 4 times minus 7 is going to give us minus 28. Outer is plus 20i. Inner is plus 21i. And then last is minus 15i squared. Remember that I is the square root of minus 1. That's the way it's been defined. So I squared then equals minus 1. So I can change that then for minus 1. So my next line is going to be minus 28 plus 20i plus 21i. And then that's times minus 1. So that's a plus 15. So here are the two real parts. So that gives me minus 13. And then the two imaginary parts are here, plus 41i. Dividing one complex number by another. If you have a complex number a plus ib, then the complex number a minus ib is called the complex conjugate of the first, and vice versa. So minus 2 plus 5i and minus 2 minus 5i are complex conjugates, and the conjugates are very useful for whenever you're dividing and things like that, and for other stuff as well. Minus 2 plus 5i is a complex conjugate of minus 2 minus 5i, and minus 2 minus 5i is a complex conjugate of minus 2 plus 5i. The deal is you change the sign of the imaginary bit. If z is a complex number, its complex conjugate is denoted by z with a wee star up above it. When you multiply a complex number by its complex conjugate, the result is always a real number. It's a wee bit like that wee trick in surds that you've done last year. If you want to rationalize the denominator of 2 plus root 3, you would multiply top and bottom by 2 minus root 3, and that gets the surd bit to disappear. It's exactly the same as this. If you multiply this by this, you get minus abi plus abi, so the two imaginary bits disappear, and you just end up then with a squared plus b squared. That's the trick then whenever you go to dividing two complex numbers. So if you're dividing two complex numbers, you effectively multiply top and bottom by the conjugate of the denominator. So let's do it here. So we're going to have then, I'll go up a wee bit so a bit more space, 2 plus 3i, 1 minus 2i. The complex conjugate of this is 1 plus 2i. So I'm multiplying top and bottom then by 1 plus 2i. So our top line then, we need to use FOIL for that. Let's just take it nice and slowly. We're going to give 2, and then outer is 4i, and inner is 3i, and the last then is 6i squared. That's all going to be over. First is 1 outer plus 2i, inner minus 2i, see how those are going to cancel, and then minus 4i squared. So our top line tidies up to give us 2 plus 7i minus 6. Hopefully you see where that comes from. Remember that I squared, this is minus 1. Bottom line is going to give us 1. I squared there is minus 1, so times that by that. The 2i bits disappear, as in 1 plus 4. So that gives us minus 4 plus 7i all over 5. And if you want, then we can write that finally as minus 4 over 5 plus 7 over 5i. And that's how you go about dividing two complex numbers. Let's look at our second example, because related to that, we'll see if we can get some sort of answer to that. It says show that this is real. So by real, it means that all the i's should hopefully cancel each other out. And we can see then hopefully what's going on. So these two are divided, so we need to find the complex conjugate of this, which handily is going to be this. So we're going to multiply top and bottom of this one by 3 plus I. We're going to multiply top and bottom of this one by 3 minus I. So that's then going to equal, let's see, 1 plus 2i all upon 3 plus I all over 3 minus I, 3 plus I. So that's my first fraction there. Hopefully you see what I've done. 1 minus 2i upon 3 minus I all upon 3 minus I, 3 plus I. It's not a common denominator. We can multiply the whole thing out and kind of do it then as a common denominator. Let's do that. Hopefully it won't be too much for people. Let's get our 4 terms here. In fact, we'll do this kind of as 3 terms. 1 times 3 is 3. Inner is going to be 6, is 1, so it's plus 7i. And then plus 2i squared. We're going to add that to this one up here. That's going to be 3, that's minus 6, that's minus 1. So that's minus 7i. And then a plus 2i squared as well, because minus times are minus. Gives a plus. On the bottom line, we are going to have 9 minus 3i plus 3i, so those bits are going to disappear. And then minus I squared. So let's tidy up a wee bit further then and see what we have. Top line becomes 3 plus 7 minus 2, because remember that's minus 1 there. Plus 3. Sorry, I made a mistake there. It should be a 7i. Apologies. Minus 7i minus 2. And then that's all over 9. I squared is minus 1, so that's actually then a 9 plus 1. So everything kind of cancels out here. That's going to cancel with that. That's fine. Then 3 plus 3 gives me 6 minus 2 minus 2. Which gives me a 2 on the top. 9 plus 1 is 10. And so the answer then is a fifth, which is indeed a real number. And so that's us.